In this video, we are going to talk about EMC, or to be specific, we are going to improve design of this power supply, which is failing EMI. Down here, you can see this red measurement. This is the measurement of the original board, and you can see it's really going very high above the limits. The limits are these red lines. And in this video, we are going to make some improvements. And after every improvement, we will measure this board again, so you can see what influence every change will make on this board. And we are going to play with capacitance. For example, we are going to increase capacitance. We are going to add additional capacitors. We will also try some filters, and also we will do some simulations so we understand better how to improve these results. And I really hope you will like it, because this is going to be very practical video. Once we make our improvements, these are the results what we will get. So these purple measurements are the measurements from the original board, and these green measurements are the measurements after we improve the board. And you can see the green measurements are nicely below the allowed limits. I'm not an expert for EMC, so in this video we are going to talk to Min. And Min has a company for EMC consulting, and also he has this website with some tips about the EMC measurements. And as usual, I had a call with Min, which I recorded, and that's what you will see in this video. In the beginning of this video, we are going to talk with Min about switching power supplies. And if you would like to jump just to see the EMC improvements, what we did, you can do so. Okay, I will mark the chapters in this video, so you will see where EMC is starting. And if you like, you can jump there and just watch the EMC improvements. But I would like to say that talking about this switching power supply design and understanding what are the important parts in the design and why we are having problems, how we can improve these problems, that's everything what we are going to talk about in this first part of the video, and it may help you to improve your own future designs. Okay, so if you like, you can jump to EMC part, but I would recommend also to watch the first part of this video for better understanding why we are doing the improvements and where we need to make the improvements. So that's everything for introduction, and I think we can start. So here is my call with Min.
This color showing, let's say, light purple or pink, is the very original results. So that's the results from this PCB. Yeah. Then this purple one here is the final results.
Yeah, I understand. But the original one, does it mean it's failing because there are the limits?
Yeah, so this line is the limit. This line is the limit. Yeah,
and it's above the limit.
It's above the limit, yes.
So they actually sell a board which is not really like not passing the EMC or EMI test.
I haven't tested this one, test against the, say, home appliance products limit. So the limit we show here is a limit
for automotive. Yeah.
Yes, it's for 25 class.
And for a home, it's a little bit higher.
Yes, but I'm pretty sure it will fail the home appliance limit as well if it's tested against it. Yes, yes.
Good to know.
Yeah, the reason I selected automotive limit is because it's one of the most stringent ones.
Yeah.
So I wanted to show our audience that, just by selecting a few filter components and by applying them correctly, you can achieve good EMC results.
This is really good because very often, even when we do EMC or EMI, then we always go for the strict one because you never know where they are going to use your products. And also, when it is properly designed, it should not fail any of this.
Yes.
If it's failing, it means there is something wrong. And maybe you don't want to sell it. Maybe first you would like to fix it because then people may have problems with your product.
Yes.
Okay. So I'm thinking we could start. So basically, I remember our first call, and we were talking about what kind of video or example what we could talk about and make video about, and you come up with this idea, find power supply somewhere on internet, buy it and measure it, and let's see if we could improve it. So I guess this one, what you have here in this PDF, that's the power supply which you found.
That's correct. Yes.
How did you choose this one? Like you just had a look and you were like, oh, this is going to fail.
That's a good question because I believe most of the power supply units you buy from Amazon, they will fail the test. Although sometimes they claim they pass the test, but if you really test them, you will feel they fail the test. The reason I selected this one, actually, I spent some time trying to select a one because this one is good in the sense that I know it probably will fail the test, and also it's a rather large PCB. Sometimes you can buy the very small size PCB, which makes modification more difficult for me. This one, the size is good size, and the layout you can, or later I'll show you what we call the paper exercise. So basically, we have a look at the layout from the top side and the bottom side. And you will see that there are good and bad design of this DC-DC converter. So I know that if I change some components, if I make some change, there will be improvement. So yeah, it's not like I selected one randomly. I still have to look at them and then compare and say, okay, actually this is the one I would like to have. Yeah.
So theoretically, you can just have a look on a board and then you can say like, this one doesn't have like the best design and it may be failing just by looking at the board.
That's correct. Yes.
Okay. It's what, $5? £5, £6. Yeah.
Yeah, £6. Yeah.
And so this is the only one which you bought, or you bought several of them?
I bought several. Yes. Yeah.
And the other, did you test also the other boards?
Yes, I tested some of them, and most of them failed. I also tested one, which is the mains, from 230 volts AC to 18 volts or 24 volts DC one. That one, when I opened it up, I looked inside, I know, it's really like this. It's gonna fail. But that one, because that one is, we're talking about high voltage. So I don't want to show to our audience because it's in a way you encourage your audience to deal with high voltage stuff, which is very dangerous. So I think this one, from 12 volts to 5 volts, we're dealing with low voltage, and then because it's low voltage, we can select stringent automotive test standards to test against. So this is really perfect example for this project. Yeah.
This is also interesting because basically it's only 12 volts, and theoretically there should not be like big problems when you design something like this. And And I think it's a really good example to show people that even designing this simple circuit for 12 volts can actually cause a lot of headaches for EMC or EMI.
That's correct. Yeah.
Okay, so what is your setup, or how did you connect this board?
Mm-hmm. So setup is showing here. So this is the system diagram of the what we call pre-compliance EMC test setup. Pre-compliance EMC test setup is something we do, as a EMC engineers who test a product in our house. So we don't have the standard shielded room, but we also wanted to test the performance. So what we call this test setup as a pre-compliance test setup. And the test setup is very straightforward, as you can see from this diagram. We need a ground plane. So often this ground plane, you can have a very large area of copper or steel, as long as it's good conductive, ground plane. And then on this ground plane, we set up the DUT, device under test. In this case, it's the DC-DC module. And then we have what we call LISN module. So LISN stands for Line Impedance Stabilization Network. Effectively, LISNs are just one filter. You can treat it as a filter. The purpose of having this LISN is to block any noise coming from your power supply unit. So the measurement, which is measured from this point, is the noise measured from this device under test, not any, you probably still have a little bit noise coming from power supply unit, but it will be limited. So the LISN basically links the power supply unit and the device under test. But in this case, again, I think just like many of our audience, we often cannot afford to buy a very, very good quality power supply unit. If you look at the proper test house power supply units, they can easily cost thousands of dollars or maybe tens of thousands of dollars just for a very good power supply unit. But there's a way of going around it. So basically, in this case, I have a power supply unit, and if I don't test this device on the test, I can see noise coming from my power supply units affecting this measurement. That's why I also put an inductor here and a common mode choke here. So these two basically filter all the noise coming from the power supply unit. So together with this filter and this LISN, I know that the noise I measured from this point is predominantly coming from the device on the test.
Mm-hmm. Mm-hmm. Okay, and in the power supply, it's like standard power supply, 12-volt power supply.
That's correct.
And 2-ohm resistor is just some... okay, I see the 2-ohm resistors.
Yeah, so this is the device on the test. This is a load, because I wanted to load the converter. You don't want to heavily load it or lightly load it. So I just choose 2 ohm in this case because of the 5 volts output. And you can see these are the LISN module I just mentioned. So they are serving as a filter block. This is my power supply unit. And this is my spectrum analyzer. And as you can see here, I have a transient limiter here and also some attenuator, simply because this device here, if you don't use the transient limiters and attenuator, the noise level is way, way, way too high. It will damage the RF input of this spectrum analyzer.
Okay, so what were the initial measurements, what you did?
So the initial measurement I did is...
On the first slide, I think I've seen...
Yes.
The graph, now, the results.
Yes, the results. Actually, I have prepared something just in case. So here we have the conducted emission and radiated emission explanation, but we can talk about it later on. For the initial results, this is our first scan. Yeah.
So what do we see here?
what we see here is, first of all, is the red line indicates the test limit. In this case, it's the CISPR 25 class 5 conducted emission limit. And as you can see, the noise level, if we look at the peak, this is a scan, average scan. So for EMC tests, normally we do average scan, quasi-peak scan, or peak scan. So in this case, I'm just doing an average scan. But as you can see, the average scan exceeds the limit by almost, in this case, 30 dB exceeding it. And you can see it's exceeding the limit from 150 kilohertz until more than 100 megahertz. So it's failing literally every single frequency point.
Nice. You choose the correct power supply for this video.
That's correct.
My next question would be, how is it possible that we can make these measurements and we don't need any antennas? You know, because usually when you go to EMC house, usually they have this huge room, empty room with the cones and antenna, and that's how you normally do this EMC and EMI measurement. So how is it possible that you can do it in your lab?
Yeah, that's a very good question. So I have prepared 2 slides for it. When we talk about EMC tests, first of all, there are 2 main types tests. One is called emission test, which tests, your interference to other circuits operating near you. That's what we call emission, because you can call it emission test, emission test basically. And then there's another test is immunity test. EMI stands for electromagnetic interference, so that's more about interference, or just to say emission. And then the other one is immunity, and the immunity is really test just how good you are, as a component yourself, not being interfered by other components. And in this case, we are testing the emission. And on the emission test, we also have 2 main tests. One is called conducted emission, and then the other one is called radiated emission.
So conducted, it means that's the situation when you are connected and you're measuring on these cables and everything. That's why it's called conducted.
That's correct. And radiated emission test is often when you have an antenna to pick up the noise from certain distance. It could be 3 meters or 1 meter or 10 meter. Yeah. So mainly 2 types of emission tests.
And what does it mean? Does it mean if you, for example, fail conducted emission, does it mean that you normally or usually also fail the other tests?
That's a very, very good question. Yes, most of the time, if your module failed conducted emission, you will have, I would say, 90% of chances of failing the radiated emission. And the reason is because, as I show here, so if we look at the conducted emission setup, as we set the conducted emission most of the time is using LISM module, and you are measuring the noise from this point. And if we look at the noise from current point of view, we can divide the noise current into differential mode noise and common mode noise. So as I draw here, the differential mode noise is the noise that you have, your current basically is differential as a pair, where the common mode noise is your current is referred to a common reference. This common reference could be, in reality, could be anything. It could be a conductor nearby, could be a component nearby. But in a test, the reference is the ground plane we use. So if you look at this, the purple line here shows the current, the common mode current in in the system. And you can see the reason we call it common mode is if you look at these currents, they have the same direction in your DC-DC circuit, whereas the differential mode has the opposite direction.
This is a very nice picture, actually.
Mm-hmm.
So this is very nicely explained the difference between differential mode and common mode noise.
Now let's just look at the radiated emission before I forget.
Okay.
So the question you ask is, why most of the time if a unit failed conduction emission, you will also fail the radiated emission. So I just have this drawing here. When we talk about radiated emission, there are many possible mechanisms that can radiate. For instance, your PCB itself could radiate. I think I remember one video you did with Eric Boganti, you guys were talking about if there's a gap on the return plane, what's going to happen. And at the time you discussed that, if there's a gap on the return plane, then you basically effectively create the voltage source. And again, the same thing, if you have a ground plane and you have a gap, this ground plane, generates the voltage source in the middle, and then your PCB basically radiates as an antenna, patch antenna. So that's one mechanism that radiation can happen. And of course, components on the PCB can also radiate. For example, in this case, the inductor selected is a shielded inductor. Therefore, the radiation coming from this inductor is very small. But if you're using an inductor which is not shielded, then the winding, the end winding itself, for instance, will have a big di over dt on the winding. So that winding itself become an efficient antenna. And most important of all is if you look at this setup as the conducting emission setup, we have a DC-DC converter showing here, and it has a cable. And the purple arrow drawing here is, as just we explained from previous slides on the conducting emission, these are the common mode current. And we know that from basic radio frequency theory, if you have a conductor, like a conductor any size, and you have current flowing on that conductor, you basically are having an antenna, and then that antenna can just radiate very efficiently.
So the frequencies what this cable is going to causing problems are these frequencies going to be like some kind of tied up to the length of the cable?
Yes, definitely. So if you look at the cable itself, if you work out the length of it, you divide it, we know the speed of light, which is 3 multiplied by 10 to the 8 meter per second. Then we know at half wavelength, you can radiate quite efficiently. A quarter of wavelength radiates very efficiently. So then you can do the math and then compare the length of the cable. Then you know at which frequency point it radiates most efficiently. Yeah.
So basically, if you would be changing the length of this cable in your setup, you would be getting different results?
For radiated test, yes, definitely. For conducted emission test, you probably will have, but the difference is quite small.
Okay, that's interesting. Also, I would like to point out that when someone will be designing, for example, power supply, then the shielded inductor may be really helpful because of the reasons what you just mentioned.
Yes, that's a very good point. And I think when it comes to all these details of designing a power supply unit, when it comes to designing like an inductor, for instance, as you pointed out, shielded, semi-shielded, non-shielded will have different performance. And also the height of the inductor is also important. So in this case, you can see the inductor is actually quite flat and short in terms of the height.
Is it better or worse?
It is better for radiation, because if you have a high or tall inductor, then of course, then effectively you just increase the length of the antenna. So it's again radiates more efficiently. Yeah.
Is it important where is pin 1 located?
Sorry, say it again.
If it's important where pin 1 of the inductor is located, the start, starting point or ending.
Yes. I think lots of people probably will know this already. So it depends on how you wind the inductor. Most of the time, you start the winding process as pin 1, as you said, and then you wound around it, and your end winding is on the outside. So all the other layers basically shield your pin 1, which is your starting point. So that pin 1, in this case, is well shielded by the outer layer of the winding. So you would definitely put that pin 1 to the noisy node, which we will show later. There's a switch node, which is very noisy. You connect the pin 1 to that node to reduce the impact, basically.
Okay. Okay, then don't forget to remind me to mention this.
Yes.
Okay, what do you have on the next slide?
Okay, so this is the part I told you that the first thing I had this DC-DC converter. I just look at it and I can point out the pros and cons of this DC-DC converter. So in this case, the good design of this DC-DC is they use aluminum electrolytic capacitor. They use the shielded inductor, as we just discussed, and it's a synchronous buck converter. So it is, in terms of performance, is probably better than one MOSFET plus one diode. But the downside of this design is the input capacitor, which is here, is very far away from the switch, which basically will increase the hot loop area, which we'll show you later. And the switch node has a very large copper area. Again, there's detail coming following. And the MOSFET is not laid out properly.
So they are like far from each other, and the connection between the MOSFETs and inductor is very large. That's what we will see.
That's what.
Okay.
Yes. Then on the back side, we can see a solid ground plane, which actually is quite good. They have a ground plane, but the downside of this design is just only 2-layer PCB, and we know that for 2-layer PCB, often in terms of EMC performance, it's generally very difficult, to design it to compare with a 4-layer PCB.
Okay.
So what do we mean by we say hot loop area? So the hot loop area is defined as the area, if you look at it, from the main energy source, which in this case is the electrolytic capacitor, and to your switches. So in this case, it's a buck converter. The two switches are like this. So the hot loop area is defined as this area. And the switch node is this point. And this point, as you can imagine, when the DC-DC converter is operating, this point sometimes connected to your 12 volts, sometimes connected to the 0 volts. And the rate of change depends on your switching speed and switching frequency of these two devices. So this node is bouncing between 12 volts and 0 volts at a very high speed. So that's create lots of noise. So that's what we call the noisy node. And as we said in the past, that if you have a inductor, you would be better off if you place that pin 1, which is inside or the starting point of your winding, to this switch node, because then the outer layer will shield this switch node. And when we say large loop area, as we can see from this PCB. So in this case, I lift the inductor. So I lift it, and I also lift this MOSFET, just purely to show you the loop area. So the loop area really starting from here goes all the way and coming all this long track, and then here they have vias to go to the backside, connecting to the ground plane. Yes, so it's a very large loop area, and the switch node area. If you look at it, I'm not sure if I can.
I can see it. Maybe you can control.
Yes.
And wheel on the mouse.
Yes. Yeah, the copper area actually is very big. Yeah, because I think it is for thermal reasons. Oh, actually here.
Yes, I see it there,
yeah. Yes. So that large area of switch nodes is again propagates lots of noise, radiates the noise outside.
So when we are designing switching power supply, we would like to keep this node as small as possible, but still be able to carry the currents what we need to deliver.
That's correct. Yes, it's always a trade-off between thermal design and EMC design. So there are many ways of reducing the size of a hot loop. The easiest way is to through better layout. So for instance, in this case, if they can move the input capacitor, get it closer, then you reduce the hot loop area. Another way is if you have a hot loop area somehow on the first layer, and it's always good to have a solid continuous ground plane underneath it. And the purpose of the solid continuous ground plane underneath actually have two main purposes. The first purpose, well, actually, I think for reducing the hot loop area, the main purpose is that plane. If you look at a current going on top layer, it will generate magnetic field. And that magnetic field will also show on the layer beneath it. And it will induce eddy current. And that eddy current, according to Lenz's law, will create another magnetic field, basically cancel out your top magnetic field. So that's why if you have a solid continuous ground plane underneath, it will cancel out lots of the magnetic field created by this hot loop area. But how good that cancellation is really depends on how close your second layer is to your first layer. So in this case, as I pointed out, it's a two-layer PCB. If you measure the distance between the first layer and second layer, it's above 1 millimeters. We know that for a very good four-layer PCB, the distance between first layer and second layer is much, much smaller than this. So in terms of the field cancelling, as we just discussed, this PCB is not good.
So it would be better if, for example, there is a 4-layer PCB and the second layer would be very close under this hot loop.
Yes, you would normally for such switch loop power supply design on the first layer, you can even have some cut off area to segregate this noisy area, because all this area is quite noisy, as we just explained. It's dancing between your Vin and 0 volts. So you have a good separation between the noisy part and the quiet part on the top plane. And on the second plane, you put a solid continuous ground plane underneath the hot loop area for the reason we just explained before, to cancel that field. And then
the noise will stay local.
Yes. So the noise won't penetrate into any other layers, let's just say. Because some people would, because I've seen people say, oh, actually, I'll leave a cut-off area on the second layer. But then that means your noise can penetrate into your second layer and affecting your third layer performance.
I think there is some kind of discussion on internet about if cutting out for example, some area under inductor, if it's going to improve or not improve performance and EMC and EMI of everything.
Yeah, I think we can maybe have another session on that, because I have I've done quite a bit of research into that area. It also depends on how you lay out the inductor. Vertically or horizontally, you will have different results. Yes.
Is there something important also about this connection between the transistor, inductor, and the output capacitor?
Actually, the output capacitor in this case doesn't matter that much because this is a buck converter. If it's a boost converter, then output capacitor design is more important.
But it's not important, like place it close to the inductor, or?
Well, if you can, of course, keep it close is always good. Yeah, you don't want to have an inductor here and then long distance have a capacitor. Yeah.
And the reason is?
The reason really is just for, I guess, it's just for design, compact design. Because in this case, the ALC is part of the circuit, isn't it? Yeah. But again, I think for buck converter, the trick is always on the front end of the design, whereas in the boost converter is like a mirror image of buck. So for boost, the output circuit design is much more important than the input design.
Okay, that's interesting.
Yeah, so, because really you just need to look at the switch node. So where, in this case, the switch node really is on the input side. So you just to be careful about the input design. Whereas, of the boost converter, the switch node is on the other side. Yeah.
Okay, what about the value of the input capacitor?
So in this case, the value of the input capacitor, yes, that's I'm going to show you. Let's have a look. So we now explained what is a hot loop area, what the visual inspection of this PCB. Basically, we just did the visual inspection of this PCB. Now
you have some. Sorry for interrupting. You have some pictures below the schematic. So before, one.
Yeah.
So yes, this one. So before we move to the next one, if we could explain what you have there.
Oh, this is really just to it's a very simple illustration. Basically, what I'm saying is, we have currents going through this loop for sure, and this is like you have a conductor and then you have current going through it. Then you will have magnetic field propagating, into surrounding circuits or into the air. So that's what we call radiation. So this is really just to demonstrate if you have a loop, and
so that's the loop antenna on the picture below. That's the These are the currents which will be flowing in this hot loop area. And this is just to show that it's going to create antenna.
That's correct.
Okay.
Yes.
Okay. So we can move and talk about the capacitor, because I'm curious to know what is the right value, and then what are the parameters or properties of these capacitors.
So this is the result of the first scan. We see it's quite bad, and what we can also tell from this result is they failed even in a very low frequency range. Most of the time, if we have a very good design, and if they fail, and most likely it's going to be fail in a, say, at least 20 to 30 megahertz range or 100 megahertz range. But in this case, the fact that this module failed even in a 150 kilohertz range indicates that they have lots of differential mode noise, and is surely to do with the loop area inductance. So what we're saying is their capacitance value, either they have very big impedance in that capacitance path, or they don't use sufficient capacitance value. So in order to prove that, we're using oscilloscope to measure the input voltage, the output voltage, and switch voltage. So this is what we set up using an oscilloscope. And for fast speed measurement, I would always stress that I never really use crocodile connection to ground. So I always use the shortest leads as short as I can. This also reduces the loop inductance of the measurement itself. So the setup is like this, and the result is like this. And as you can see on the input capacitor, you can clearly see a voltage ripple, and it is quite big. It is the same as the switching frequency.
So the blue one is measured on the input capacitor.
Yes, so input 12 volts capacitor, that's the voltage ripple measured. And the red one is on the output voltage. And the green one is the MOSFET, is the bottom MOSFET switching waveform.
So what we need to do is make the blue one more straight.
That's right. That's right. So the first fix is okay. Yeah, this is just the details of this. So I did also use the oscilloscope to do the FFT, and I found, this is the switching frequency, same as the MOSFET. And yeah, so the first fix is they are using 100 microfarad capacitance. So I'm just going to increase that capacitance to a 330 microfarad, and just to see the impact on the EMI, EMC noise spectrum. So in this case, I replaced the original one. I put a 330 microfarads on the input. And here's the result. As you can see, the green trace is the previous scan. And the purple one is the one with the 330 microfarad capacitance. You can see there's a 10 dB reduction from the low frequency range, from 150 kilohertz up to about 10 megahertz. So really, the capacitance helps on the low frequency range.
And is it because then a capacitor will become inductor for higher frequencies?
Yes. I also prepared a slide for this. Yes. Okay, so this is the 12 volts measurement. Once we replace the capacitance, you can see the ripple is becoming less, but still you can see, it's not a straight line. Okay, now, before we answer your question, let's try another one. Yeah, I think this is interesting. How about we put two 330 microfarads in the front. So now in this case, I just removed the other connector and I put another 330 microfarads. So effectively, we now have 660 microfarads and results. Okay. In this case, the top trace is the first scan with no fix. The second trace is with one 330 microfarad capacitor. And with two, again, you bring down another 10 dB, almost another 10 dB. And it's also effective against to about this level. Yeah, high frequency. Well, actually, you can see here, high frequency, in terms of high frequency performance, is also improved by about 10 dB.
Ah, really? Wow.
Yeah. So the first one actually didn't improve the high frequency performance.
Can we go back to the other one?
Yeah.
Ah, that's big difference.
Yes. So the first one, if you look at from say 30 megahertz to 120 megahertz, there's no visible improvement. So you can see this point is about 60.
Yeah.
And this one, you can see with two 330 microfarad capacitor, it helps on the high frequency range.
Is it because we use two capacitors, or if we would use one 660 microfarad, we would see same result?
It seems like you can read my mind. Now, okay. Before that, let's do more tests. Okay. We mentioned before that reduce the loop area will help. So in this case, now I'm moving this newly added 330 microfarad capacitor a little bit closer, So I basically scraped the copper area here and copper area here, and I soldered this one closer. Okay. And let's have a look. Let's have a look. Aha. So in this case, the green trace is the previous result, 2 330 microfarad capacitor. The new trace is with 1 330 microcapacitor, but moved closer to the switch.
But isn't there also another one? If you go up, then you still have there 2 capacitors, no? There is also...
No, I just moved this one to this one. So
okay,
still
so there are still 2 330, just one is closer.
Yes.
Okay.
And you can see that from low frequency range, you barely see any difference. But on the high frequency range, look, you achieve about 10 dB reduction.
Because we change impedance.
Because we change the impedance. That's from the circuit point of view.
And we also make the loop smaller.
Smaller, yes, yes. Now, your question, how about 1 680 microfarad capacitor? So let's have a look. Now in this case, I removed 2 330 microfarad capacitor, and I put a 680 microfarad capacitor. So, if you think about it, 2 330 you in parallel, that gives you 660. And now I have 680. Surely I would expect a better performance, isn't it? 680 microfarad. And let's have a look what happened. So again, this is the previous scan, which is 2 times 330 microfarad. But look at the 16080 microfarad. The performance actually is getting worse. It's getting worse. So let's have a look. Why is that the case? So why 230 beats 16080 microfarad? If we're using circuit view, which is what we were taught in school, everything, we treat every circuit unit as a capacitor, inductor, a resistor, then we can also explain, because we say, oh, look, 2 330 microfarad capacitor, you will have 2 inductors in parallel, which is the ESL. The ESR will be in parallel. So overall, you reduce the ESL and you reduce the ESR. Effectively, you reduce the impedance in the loop, so your performance is better, which is the easy, simple way of understanding it. Okay, so what's fixed fine? Okay, so we just experimented with increasing input capacitance value, and we compared 2 330 microfarads against 1 680 microfarads. But the performance still not good. We're still all over the limit, right? So the next step is to explore a filter. So in this case, I'm building a LC filter, because a LC filter is a low-pass filter. It's very effective in terms of filtering the differential mode noise, as we just discussed. So in this case, I removed one of the 330 microfarad I added. So I still use 330 microfarad capacitor. And then I have
the one which is close to the transistor?
Yes, the one is close. Yeah, so I removed that one, and I put an LC filter in the front. So the LC filter I put in the front has this value, and I have a simulation. So I run the simulation, and I can see the attenuation from 20K to about 20 megahertz is quite significant attenuation, more than 60 dB. So I know that this filter is good for the noise we're looking at. So that's the filter configuration. And then we test it. And this is the result. This is the, yes.
And where is the reference signal 2 times 330 microfarad without front end filter? Okay, that's the previous one.
Yeah, so this is the previous one.
So do you have picture of this board?
We have picture. Yes, we should. Well, because here I just wanted to show the
Okay.
LC filter. Yeah, so I put in here. Yes,
Okay.
I put in here. Yeah.
So the 330 microfarad, it's the one which was there originally, or it's the one
Yeah.
which is close to the transistor.
Okay. Yeah. I see what you mean. So I basically, I removed this one.
Okay.
Yeah.
So it's
Yeah.
the original board, but with filter.
Yes. And you can see now, finally, we have limits actually below the limit. Oh, sorry, we have the result, which is below the limit line now. Yeah, so they are all now below the limit line. However, from 30 megahertz onwards, it's still failing. So we actually achieved good results. And actually, as I pointed out here, because all this test setup, I'm using 33 dB attenuator altogether. So now I know that the noise level is lower than the limit. I can get rid of those attenuator because then we can see the results better. So, so in this case,
I'm sorry for interrupting. I'm just thinking the original capacitor was even lower. It was not 330.
Yes, the original one is 100 microfarads.
Okay, okay. So we increased the value to 330, and we also added the filter, and that's what was enough to basically pass for these low frequencies.
Yes, that's correct.
So you don't need to increase like frequency, sorry, capacitance too much. We don't need 660 microfarad.
No,
we just need the filter.
Yes, because in this case, the majority of the noise is blocked by the impedance of this inductor. Yes. So rather than adding this capacitor value, by a large value, what you need is you need a small value inductance value just to achieve that attenuation showing here.
What does it means that the inductor is not going to, or the filter is not going to allow the noise to come out of the board?
That's correct. That's correct. And so now we're now at a stage that I can just use this transient limiter. Now with only 10 dB attenuation, so the result will be good. And also I have this module here. It's called Listen Mate. And the purpose of this module, as you will see, is to, when we talk about the conducting emission measurement, we say the measurement often we have both common mode noise and differential mode noise. And this module here can separate the common mode and differential mode. So now we look at the noise. Yeah, then we look at the noise. We know, actually, we need to do more filtering on the common mode, or we need to do more filtering on the differential mode. So that's why I introduced this module here at this stage.
So you can measure one noise and the other one.
That's correct, yes. So now, this is just a scan because before we were using 33 dB attenuator. So now I'm using 10 dB attenuator. So we now look at this scan as a reference. This is our midpoint reference, let's say. So we can say, as we increase the input capacitance to 330 microfarads, and with the LC filter in front, we reduce the noise in the low frequency range. But on the high frequency range, we still exceed the limit. And as you can see here, this bit also, this part from 7 megahertz or 6 megahertz is starting to increase. Okay, so that's the result. And now I'm using that Listen Mate module, which can differentiate the common mode.
This is nice. I didn't know you can separate this.
Yes, you can. And for more information, Ken Wyatt, who is quite famous in the EMC world, he wrote an article of this module. So just in case everybody interested, you can just have a look how it works. So back into this result. So now I look at this result and I know, okay, indeed, the common mode noise is often dominating the high frequency range, yeah? And the differential mode is actually dominating the low frequency range. So now what we do is we need to try our best to suppress the common mode contents.
How do we do that?
So how do we do that? Yes, let's have a look. Now, the approaches now we apply is still differential because I'm adding more capacitance between the V-in and the ground plane. Yeah. So as I show here. So I thought we're talking about suppressing common mode noise, but why are you applying a differential mode capacitor again? When energy was delivered, if the energy is not delivered, immediately, the energy is basically, as a nature will never read labels. So nature would not say, oh, actually, I need energy and I only need energy from that capacitor. I'm going to ask that capacitor for energy. No, it will say, if there's a nearby energy source, when we say nearby energy source, it could be a small capacitor nearby or a chip nearby or a conductor nearby. There will be some sort of energy stored in that structure. So when the load requests energy, it will request energy from everywhere. And it's the fact that when the load asks energy to be delivered from everywhere, that creates the common mode noise. So from this point of view, if I can deliver the energy immediately from differential point of view, I will still be able to suppress the common mode noise. So basically what we're saying is, to put it simple, is sometimes common mode noise will create, sometimes differential mode noise will create common mode noise. So that's what I'm trying to do. So in this case, I'm applying a 10 microfarad capacitor between the V-in and the ground plane, okay? And then see what happens. And this capacitor I'm choosing is from Worth Electronics. And this is the impedance against frequency curve of this ceramic capacitor. And I know that it should be very effective from 500 kilohertz to about 20 megahertz, because here you have the least impedance of this capacitor. And let's have a look at the result. So as explained, from 500 kilohertz to 20, 30 megahertz, I've seen big reduction.
Wow. Yeah. You just add one small 10 microfarad capacitor and this is the difference.
That's the difference. And that's why I said initially I said, you want to deliver that energy immediately. And this ceramic capacitor basically provides that. Yeah. And the effect really starting from 500 or the 800 kilohertz all the way to above 100 megahertz, although we still fail in this region, as you can see here. And these spikes, we can ignore this because these spikes actually are BBC Oxford, because as I said, I'm testing this in my house. I don't have a shielded room, so I will pick up these spikes. But if we look at the main profile, so we're still exceeding limit here. And interesting, I would point it out, is from the low frequency range, if you look at 150 kilohertz to 1 megahertz, you see the noise actually increases. You see the resonance point increases. Why is that the case?
It will make some, it's inductance plus the capacitance. It makes resonance at some frequency.
Yes. So that's the problem of ceramic capacitors, is that they tend to resonate with the structures in your design. On the PCB, it could be a track. Any track could have an inductance between 5 nanohenry, 15 nanohenry, and just resonate with a capacitor. So this is quite common. And the way of dealing with this resonance is you either add a small damping resistor or you choose a different value. So in this case, if I choose a different value, 4.7 microfarad, you will see that that resonance basically is reduced.
Wow.
But I didn't lose any performance from the high frequency range. I still have the same performance, and I reduce the resonance.
This is really cool.
This again proves the point we just said. When it comes to ceramic capacitance, don't always look at the value. Think about it's the energy you want to deliver efficiently. So it's not about the.
So you would like to place enough capacitance, but not too much, because if you place too much, then you can actually create some resonances which can cause problems in lower frequencies then.
Yes. So then the next fix is to put more capacitor, as lots of people often do, because it's a very good technique. It works lots of times, because when you put different values of capacitance, in this case, for instance, I put 4.7, 470 nano, and 150 nanofarad. So I have 3 different values. And if I look at the impedance against frequency curve, you can see I have low impedance from 1 megahertz to 10 megahertz. And then again, I have another low impedance. And then again, I have another low impedance.
So when you say low impedance, it's like 100 milliohms. That's low impedance.
So the low impedance often is the impedance value close to the self-resonant points of ceramic capacitance. So what you want to do is you select 3 or 4 or 5 capacitors, and that resonance point cover each frequency range. So overall, you achieve a frequency range like this.
In wider frequency
range, yes.
Is not this going to make more problems in the lower frequencies?
Not necessarily. Often the resonance is caused by the bigger value capacitor.
So if you use smaller one, then it's not going to interact with the structure of the PCB, or.
Yeah, not often. Often. Yeah. And so the reason that's how I selected these 3. And then what I did next is I have a simulation model, which I might show you here. Let's just see if I can find it. Yes. So this is the simulation model I create. As you can see here, this is the L, which is the 4.5 or 4.5 microhenry inductor we use. This is just the equivalent circuit. I put some parasitic capacitance, some resistance here.
So that's the filter, 4.
That's the LC filter we applied. Yeah, that's the LC filter we applied. And
on the other side, okay.
Yes, yeah.
Okay, and, so the input is on the right side now. And
let me explain it. Yes.
Okay.
So otherwise it's confusing. You're right. Let's have a look at let's look at this one first. So in this case, this one is purely a noise source. Okay, so I'm just creating a noise source, and I knew previously we have 330 microfarads put in the front, so that's connected, and then later we put an LC filter. Yeah. So basically, this noise source you can think this as our switch node. That will make sense. So this is our switch node. This is our input capacitor. This is our LC filter, and this is our measurement. Yes.
Okay.
Yes.
I understand. So we are going from left to the right, and on the right, basically, there is like our input power supply. If we go further, there would be our input power supply.
That's right.
Okay.
That's right.
And on the left, there is our load, basically.
Yes. But in this case, that would be. But in this case, I should say that I'm not simulating the DC-DC converter. I'm simulating a noise source and filter performance.
I understand now, yeah.
Okay. So now, what we did just now is we effectively put 3 different values of capacitor, isn't it, next to the noise source, and we wanted to see the difference. So if now I run this simulator, and as you can see, so the blue one is a reference one. So so this blue one is literally like no, it's not our filter configuration. The green one is our LC filter, as we showed before. So we can see the LC filter has a big attenuation from low frequency to 100 megahertz. But you can see the added capacitance only improved a little bit, really a little bit. If you look at this, we're talking about 20 micro, 5 micro. It's 4 times, 4 times is less than a few dB. So this improvement, what it translates into the measurement is that we probably won't be able to see any change in the setup we measure, because it's only really a few dB difference if you look at it. Whereas, previously, if you just look at this LC filter we talked about, we say it's 40 dB at least. So that's why when we have the sorry, I think the wrong. What's this? Oh, I think I missed the slides here. But the slides I wanted to show is, oh yeah, actually it's here, I think. No, I missed the slides. So basically what we're saying is adding...
It would be very similar as the number 33.
Yes. So I also tested it. I can't see any difference. See any difference. Yeah, simply because, if we look at the simulation results, the improvement is really limited to a few dB. So we can't see any difference.
So 10 microfarad capacitor is enough?
Is enough, yes. So what can we do with this part? Again, now I'm using the listen mate module again. So I'm looking at the differential mode and common mode. And I know, okay, with this result, all I have to do is to do with this high frequency common mode noise. Yeah. So this is the part I need to deal with. And for common mode suppression, many EMC engineers will use something called a ferrite core. So a ferrite core basically is a magnetic material that acts as a common mode filter, as shown here. So in this case, I'm using what we call 44 material from Ferrite. It's a company that makes all this ferrite core. And if we look at the impedance against frequency curve, we see that it is quite effective around 100 megahertz range. Yeah, so 100 megahertz range. So if I put this ferrite core in here, I'm expect to see the noise around this region would drop. So this is the performance. The reference signal here is the previous results, which exceeds the limit. And the green one is the one with the common mode choke. It's the ferrite core, and you can see the noise has been now suppressed below the limit.
And you place the ferrite on the input cable.
That's right. So I put
close
it here.
to the board.
Close to the board, yes.
And you just clamp it, and that's it.
That's it.
The wire just go inside or through the hole of inside of the ferrite.
Yes, because this one acts as a common mode, so it doesn't affect your differential signal. It only works against the common mode noise.
Why it helps with common noise?
I will show you later. Yeah.
Don't tell me you have another slide for this.
Yes. I know you have. I expect all the questions you ask, So, but let's have a look. Okay, so this is the 44 material performance.
I would like to go back. So the very high frequencies, the noise in the very high frequencies. What do you have? Go to the next slide.
The next slide.
Yeah. So I just would like to clarify if someone didn't hear before, the noise at the very end is coming from outside of your building or something, yeah? So you
Yes.
cannot really influence this. It's
Yes,
not coming
these are
from
just
the board.
Yes, these are the radio signals.
Yeah.
Yeah, this is the BBC Oxford. Yeah, and okay, let's go to the next one. The next one is because yeah, so we suppress the noise around 100 megahertz, and we have all this, below the limit. So I wanted just to try another one. So I picked another material. This material is called 75 material. And if you look at the 75 material, it has excellent attenuation between 1 megahertz and 2 megahertz, so even lower frequency. So I put it here just to see, what's going to happen, okay? And here we go. So this reference signal, the light purple one, is still our previous result, well, the one without the common mode filtering. The green one is the first common mode choke, and the purple one, or the pink one, is the newly result. As you can see, the improvement is little. I think it's below 5 dB improvement. Not much.
So you don't really need to use so big ferrite core.
Yes.
Because this one is much bigger than.
Yes.
But do you have both of them?
Yeah, I have both of them.
What if you remove the smaller one? Then it's going to be even worse.
No, I think, yeah, it will get worse because this one doesn't work above, you can see it doesn't work into that region, so it's not going to work. Imagine if you're an engineer and you are given the task of designing this DC-DC converter. And of course, previously you apply a small LC filter, which we know that we can easily put on board. But now you're going to present this result to your boss. You say, look, we need this big guy to help us pass the EMC test. Your boss probably will say, leave this building right now. So we can't do that, right? So the next one is, so that's what we did next. So we know that, okay, so I think the test before basically just want to demonstrate that it is really the common mode noise that we need to filter in this case. So to better filter the common mode noise, what we need really is what we call a common mode choke. So in this case, I picked up a 250 microhenry common mode choke. As you can see, the size is much smaller. And we can easily put this on the PCB if we want. So let's have a look. What does this common mode choke,
So we use the ferrite just to prove that we have problem with this common mode noise, and we need to filter it. Okay.
Yes. So that's why often if you send a sample to a test house, and those test engineers will often put some ferrite core on the cable, and then they tell you, oh, okay, if I see, say, 10 or 20 dB reduction, so they will tell you, look, you need to do something on your common mode filtering. So then as an engineer yourself, you might go back and say, look, how can I improve it? Shall I put a common mode choke, or shall I use something else? There are many ways of doing it.
How did you come up with the value?
This common mode choke?
Yeah.
That's the only one I have in the house, for this current. But generally, well, not necessarily true because I have my simulation tool. I'll show you.
Okay.
Now you're asking a question. Now I'll answer your question. Yeah. So again, this simulation model is again very simple and easy one. So this voltage source again is just to simulate the noise. And what I did, and listen in this case, is a 25 ohm resistor. Why? As if we can remember, let's go back to the beginning when we explained the common mode. If you look at the current going this way, let's just say, and then it's coming to the listen module and it is split. And we know this is a 50 ohm resistor, this is a 15 ohm resistor. So to common mode is a 250 ohm resistor in parallel. That's why we can simplify it using a 25 ohm resistor. So that's why in the simulation model, I use a 25 ohm resistor. And what what I did was, so the first is I didn't use any common mode filtering. So I just have a 150 picofarad capacitor connected here. And the next one, I introduced a 250 microhenry inductor. But this is really, of course, it's not a common mode choke, but what we are simulating here is the how do I put it? It's because common mode current goes, on both lines. So I'm simulating one line.
That's basically what I was thinking about.
Yeah. I'm simulating one line, and if the attenuation is good enough, then I know on the other line, because I have a common mode choke, so it will be the same. So that's the idea behind it. So if I run this simulation, I can see that this is the performance of this common mode. Well, yeah, this is common mode choke performance. And you can see at 100 megahertz range, it has a big reduction, big reduction. So I knew that using a 250 microhenry is very good. If I reduce this value, say if I reduce this value to 100 microhenry, you will see the curve will go like this. So you have less attenuation. So that's a very simple, easy tool for me to select a common mode choke value.
Okay.
And so with this good confidence of this value we selected, we can see the difference. So we know that with the previously tested, the ferrite cores we applied, we're already below the limit. But look, with a 250 microhenry common mode choke, it's improved a lot. It's from 10 megahertz. From 10 megahertz, we again have another 10 dB reduction. And from 30 megahertz, we are below the limit by more than 20 dB. So that's a very good margin, for your design. So of course, if you see a result like this, you probably say, oh, actually, we don't need that 250 microhenry is probably too big. We can choose a smaller value one. We'll still pass the results and probably get a cheaper part. Yeah.
Nice.
Yeah. So this is just the final result as a comparison.
This is so cool. I think it's like super useful for people to see how these small components can make big difference. And also what I found super useful is these your simulation circuits and simulations, how you simulate the filters, because many people, they may not have ideas how to simulate filter which they should use for their circuit, for example. And that's everything for today's video. I would like to say thank you very much to Min, because it was a lot of work to prepare all the materials for this video. I really appreciate this, and I would like to say thank you, Min. Now, what you think about this video? Leave comments, okay? I would like to know if you have any questions, or I would like to know if there was something surprising, if you learned something new. Let me know in the comments. If you like this video, don't forget press like button. If you would like to see future videos, and there will be also some future videos about EMC because I'm working on some. So if you would like to see them, don't forget to subscribe. I would like to thank you very much for watching. My name is Robert Feranek, and see you next time. Bye.